In this lecture, we're going to discuss two important results in homology. The first one is what we call homotopy invariance. We'll say what that means, but basically what it says is that if that homology is not only a topological invariant, it is also a homotopy invariant. And the other result, which is not as important, but it's a pretty cool result, that's what we call the Hurewicz isomorphism. It says that, and we alluded to this in the previous lectures, that there's a connection between the fundamental group and the first homology group. And the connection is basically that the first homology group is the abelianized fundamental group. And you make it a bit more explicit with the isomorphism. But before we do any of that, we have to actually discuss some convex geometry. So let's discuss something that we call convex geometry. And you might be very surprised to hear this, but this has many applications. If you're interested, there's actually a video series that is being released right now on Stanford by Stephen Boyd, and it's called Convex Optimization. It's by Stanford, and interestingly, there's something that's 15 years old. So he had his old video series on this topic from 15 years ago, but then there's like a brand new one that's being released. And that course is based on applications, so that's why it's optimization. But the beginning part of the course, you can say the first several video lectures all discuss convex geometry. And the way this comes up in applications is because, for instance, if you're talking about, let's say, if you have a team of employees and the amount of hours they work per week is not negative and they cannot exceed 40 hours per week, and the total sum of their hours has to be bounded because there's a certain amount of money that you can pay. Like when you put all of those conditions and you like draw the inequalities in Euclidean space, you get some kind of these convex types of regions that come up, and that's how it emerges in many applications. But we're going to just find it helpful for the purposes of topology. So let me start with this. So first of all, we know what convex means. We say that C, this is a subset of Rn. And by the way, we're going to be specifically working in n-dimensional Euclidean space. Convexity does not make any sense whatsoever in a topological space. So we say a subset of Rn is convex if and only if for any 2 points in C, the interval or the line segment is contained in C, where this is, by definition, you can say this is lambda p plus 1 minus lambda q, where lambda ranges from 0 to 1. These are, of course, these are vectors in Rn, because C is contained in Rn, and the lambda, this is, of course, a scalar, but we are mathematically mature enough to understand which one is which. And as you can see, if you set lambda is equal to 0, this one goes away, and that's just q. And if you set lambda is equal to 1, this one goes away, that's just p. And when you make lambda vary from 0 to 1, you're just interpolating all of the points in a linear fashion, right? This is a linear combination. There's a lambda here, and there's a 1 minus lambda there. So you're interpolating them in a linear way between p and q, and you get a line. So that's what we call convex. So the next definition that I want to write down is definition. Let's suppose x1, x2, well, I'm making them bold, but maybe I should not make them bold. x1, x2, up to some, let's say xk, are vectors in Rn. We define, let's call it convex. I'm actually not sure what the actual terminology for this is, what the actual notation for this is. But convex of all of this, this is going to be what is known as the convex whole of the points. What is the convex whole? So this is equal to, so this is again by definition. So when we write convex, you would read this as the convex whole of those points. Or you can say vectors, depending how you want to think about them. Point and vector are interchangeable. So you would just say that this is the smallest convex set which contains all those points. What do we mean the smallest? So more specifically, C is the convex whole of those points if and only if for any convex set K contained in Rn with the points being in K, we have that C is contained in capital K. So it's the smallest convex set. And as an exercise, I do not want to talk about this. In fact, I want to say this, all of the results that we're going to write down in convex geometry, we're not going to prove any one of them. And they're not difficult to prove. They're actually quite straightforward to prove. But you can think about this, like how do you prove that this actually exists? But let me just show some pictures for you. That's what we call the convex hull. So here's some pictures. So let's say we're located in R2, and you have a point over here, x1. Okay, then the convex hull of x1 is just itself. A single point is convex because if you pick any other point, you're just picking the same point, and then the line from the point to itself is just the point itself. So the empty set, for silly reasons, is also convex, but the empty set is not the convex hull because it does not contain x1. So now let's say we have another point over here, x2. Then the convex hull between those 2 points would actually just be the line between them. Okay, because if you think about this, the convex hull, by definition, has to contain the line between x1 and x2. So if you put in the line, you just created a convex set that contains those two, and it has to be contained in every other convex set. So that would be the convex hull. So the convex hull between x1 and x2 would be the line from x1 to x2, the line segment. Now, what if you have 3 points? Well, this is where it gets interesting, because it depends on how the points are configured. So if the 3 points are already in a straight line, then the convex hull would be a line. So if x1, x2, x3 are on a line, and the fancy way to say this is you say that they're collinear, then the convex hull of those 3 points is a line segment. And it's a bit complicated to say how it goes. In the picture that we have, it's the line segment from x1 to x3, but that's only because x2 is in between x1 and x3. In general, you might not necessarily know which one is in between. So you cannot more specifically say which of those two you have to pick. But this configuration that you see over here, in geometry, we call that a coincidence. It was not supposed to happen. Not supposed to happen like randomly. Basically, if you take a pen and you just mark down 3 random points, what are the chances that they form a perfect line? Right? That's not supposed to happen. We call that a coincidence. Rather, what is supposed to happen is your points, x1, x2, x3, are not supposed to be part of a line. And then the convex hull. So then the convex hull would just be the triangle formed by all of them. So that would be the convex hull. Okay, so let's say this. The convex hull. So let's say, so we say that 3 points in, let's say, R2, and you can make this more general, right? But let's just keep it simple. Let's just say in R2 are in general position. So it's called general position because this is what happens in general. So this is a terminology that I invented. This is the way I like to say it. I like to say they are geometrically independent. I think someone should, I think people should probably say that more frequently so it catches on. I think that sounds nicer than saying in general position. You have to be a little bit more careful because these three vectors, I'm going to be careful, x1, x2, x3 as vectors are linearly dependent. It's different notions because as vectors, if you draw the arrows, you can then express x2 as a linear combination of those two. So you have to be a little bit careful. Linearly independent is similar to that, but that's not really the right way to say it. There are some people who I believe they say affinely independent, but I do not like how that sounds. I'm not a fan of how that sounds. I prefer to say geometrically independent, or you can say in general position. So we say that three vectors are in general position if and only if, so this is the way you can define it, if the convex hull that you form out of that is homeomorphic to the standard two-dimensional simplex. Right, the standard two-dimensional simplex. In fact, let's describe the two-dimensional simplex in a nice way while we are at it. So if you let E0 denote the vector that has 1 in the 0 position and 0 everywhere else, so this is an Rn plus 1. So you basically, you count from 0. That's why it's n plus 1. And then E1 is the vector that has a 1 in the 1 position. So then the standard n-dimensional simplex that we write, you would just say it's the collection of points in Rn plus 1 that are non-negative and they sum exactly to 1. That's the same thing as saying that this is the convex hull of all of those points. It's the convex hull. You can actually rewrite this. You can write it in terms of that basis. You can say it's x0, e0 plus x1, e1, and so on, x and en. And then the condition is that the coefficients are non-negative and they have to sum to 1. Okay, so this is the way you can describe what. So this is what we call, this is what we refer to as the standard n-dimensional simplex. This is probably the easiest one to describe, and this is the one that we use when we work with homology. Though we do have some annoyances, because when we look at the faces of an n-dimensional simplex, that's no longer the standard simplex. So we have to take a homeomorphism back to the standard simplex and work with that. But this is the way this is the one that we use for homology. But you can really use any one of them for homology. You just have to pick one to be consistent, and this is the most convenient one to pick. Okay, now let me just say what happens more generally for a different type of simplex. So in general, if the convex hull of a bunch of points, let's say x1, x2, xk, is homeomorphic to the k-dimensional simplex. Okay, so in other words, we're assuming that these points, so these x's are in Rn. So if you assume that these points are in general position, so that means the convex hull reaches the largest possible dimension that you have. Actually, small little mistake, that's not supposed to be. I guess I should really count it beginning from 0. Yes, that would be the better way to do it. So if we have a bunch of vertices and they're in general position, then the convex hull will give you something that's homeomorphic to this. Now, let's describe this as a set. So there's a nice way to describe this as a set. So as a set, if you want to write this out, you can say that this is the collection of all points that look like this. Lambda 0, x0, plus lambda 1, x1, plus lambda k, xk. And of course, we are mature enough to understand that these are vectors, these are scalars. The lambdas are non-negative, and they have to sum to 1. So it's actually a very similar condition that we have with the standard simplex. The only difference is that when you're using the standard simplex, you just replace this by the standard basis. But other than that, it's the same idea. And furthermore, there's a homeomorphism. So what's the homeomorphism? So there's a homeomorphism from that to the standard simplex. And the homeomorphism is simply the coefficients that you're getting. Right, so this is going to be in RK plus 1 with the exact same conditions. So that's going to be your homeomorphism. So it's like I'm saying, like I'm making a lot of facts over here. They're pretty believable. I'm not going to verify these. Like for instance, why the convex hull is equal to that. So you basically argue that this set that you're getting, it is a convex set, and then you argue that if a convex set contains those points, it must contain every point of this form. And there's a homeomorphism from that set of points to this set of points, and it's sort of the obvious homeomorphism. You just take this point and you map it to those coordinates. Right? So you map it to that coordinates. Okay. Now what's interesting here is this homeomorphism depends on the ordering of the vertices. Because if you order the vertices in this way, then when you map the point in the convex hull, the first coordinate that you get, but maybe I should say the 0th coordinate that you get, that's just a coefficient in front of x0. So it will depend on how you choose to order those. But the point is, one has such a homeomorphism. Of course, if these points are not in general position, then this would be homeomorphic to a lower dimensional simplex. And there's actually an important problem in the applications of mathematics that we're not going to discuss, but it's an interesting problem that if you randomly, let's say, draw a lot of points in R2, right? So this is in the two-dimensional plane. If you look at the convex hull that you get, you're going to get something sort of like that, right? You're going to get something like this, which is no longer a simplex, right? You can see it's no longer a simplex. The way we get a simplex is when the points are in general position. Clearly, these are not in general position, but that would be the convex hull. And you can see that some of the points are redundant. So there is this problem in computing that if I give you a lot of points, how do you disregard the ones that are unnecessary and you only keep sort of the important ones in the convex hull? Okay, so if you're confused, like, I mean, you might look at this picture and you might say, that does not look like a simplex. And you're absolutely correct. But that's because we're using a lot of points. What I'm saying is, so in R2, you pick 3 points in general. So that's what you do. So in R4, in R3, you pick 4 points in general. And if you pick them in general, position, then you're going to get something that's homeomorphic to the simplex. And this is the homeomorphism that one has. Okay, so this is just a little bit of convex geometry for us. And now, how does this come up? Well, it comes up in the following way. I mean, we've seen this before. So we talk about this, the map from n chains to n minus 1 chains. Okay, so here X, this is a topological space. These are n chains. And these are n minus 1 chains. And the way the map is defined is we pick a simplex. So a simplex here is not an actual simplex, it's a mapping. So it's a mapping from delta n into X. And the boundary of sigma is a mapping from the n minus 1 simplex into X. Sorry about that. That's incorrect. I'm sorry about that. That does not. What I wanted to say is sigma has faces. So you talk about the ith face of sigma. So the ith face of sigma, you kind of want to say it's a simplex, but in homology we work with mappings. So it's supposed to be a mapping from the n minus 1 simplex into X. Okay, and then the way we end up defining the boundary of C as this alternating sum of these different faces that we get. So it's the alternating sum, and then we end up with n minus 1 chain, because it's a formal sum of smaller dimensional simplices. Again, by simplices we mean mapping, right? Mapping simplices. Sometimes they're called singular simplices because this map can have lots of singularities. But anyway, how do we define this? So this is the way we define, and we define this as you're going to take sigma and you restrict it to the ith face of delta n. So that's the way you do it. And right, you're sort of restricting it, but that's technically not correct, because when you restrict it to the ith face, it's not, you're not getting a you're not getting delta n minus 1. You're rather getting something that's homeomorphic to n minus 1. So more appropriately, what you're getting is you're taking sigma and you're restricting it to, now the way you get the ith face, what this is coming from is, recall what we said. We said that delta n is the convex whole of the standard basis. So when you're taking the ith face of that, you're going to delete the ith basis vector. So you're just going to have that this is the convex whole of E0, E1. You delete the ith one, so you get this, right? The convex whole. So you're going to get that face. So maybe to make this a little bit easier to see, if we go back to the two-dimensional simplex, this is the convex whole of E0, E1, E2. And in the picture, we have our three axes. And you can think of this one as representing E0, E1, E2. They kind of point in those directions. And the convex whole is so all of those points, they only go up to one unit in each direction. And if you want to get this face over here, if you, so let's say a convex whole of, let's say, E1, E2, so notice what we're doing, we're dropping off E0. So if you drop off E0, you're getting the convex whole between those two, so you're just going to be getting this face, right? So this is exactly face, the zeroth face of delta 2, because you're setting this one equal to 0. So that's the zeroth face. And that's the way it works. It's the convex whole of one fewer point. But recall what we said. We said that this convex whole is homeomorphic. So really what we're doing is we're being sloppy, but really what we mean is it's sigma composed with the homeomorphism from the n minus 1 simplex to this simplex. E0 all the way up to, you have EI all the way up to EN, and EI is being deleted. So that is really what we're doing. So we're writing sigma restricted to the convex whole of one fewer vertex, but we're being sloppy. More specifically, we have to compose it with this homeomorphism that we talked about before. There's a homeomorphism anytime you have points in general position. So if you have points in general position, then they're going to be homeomorphic to a simplex. So we're just choosing that homeomorphism that we described before for us, and that's really what we mean. So I just bring this up because this notation, this abuse of notation, is going to be used a lot in what follows next, and I want us to be comfortable with it. I want us to be comfortable with abusing notation, because writing out explicitly, like really carefully, makes the proof be a lot more complicated than it is, because you're hiding the difficulty in proper notation and you're masking away the main idea of the proof. So now we're going to talk about why homology is a homotopy invariance. So that's like the main result of today's lecture. Here's the main theorem of this lecture. Let x and y be two spaces, and f from x to y, g from x to y, be homotopic maps. So homotopic maps means that you can continuously interpolate f into g. If you're not sure what I mean by that, when we write the proof, I'll remind you again the rigorous definition of what it means for two maps to be homotopic. Be homotopic maps. Then the induced map that you get, right? This is the induced map. Recall what we said, homology is a functor. So anytime you have a continuous map between two topological spaces, you get the induced map. So the induced map that you get, so that's an induced map, and you have another induced map. So you have two induced maps, that these are equal. So these are equal. So if two maps are homotopy equivalent, then so they could be different maps, right? F and G in general will be different maps, but they're homotopy equivalent, then the induced maps that you get are actually the same. Now, before we prove this in a rigorous way, let's see if we can justify this by some kind of intuitive argument. So here's the way we do it. You have to recall how the induced map is defined. So you take a cycle, C is a cycle, and the way you map the cycle into this, right, what is this? It's basically composition. You do F composed with the cycle. Now this, of course, does not really make sense because a cycle is a formal sum of simplices. So maybe it makes a little bit more sense to consider what happens on a simplex. So if you have a simplex, so if you have, let's say, a simplex like this, so delta n goes into x, and then you have y over here, then the composition will give you F composed sigma. So you're doing composition. And then the cycle is a formal sum of these simplices, and it gets mapped. You just apply the composition on every simplex that makes up the cycle. And that's how this induced map is defined. And this one is defined in a similar way by composition. So here's the intuition. The intuition is that when you map sigma, when you take delta n and you map it into x, right, you're getting some kind of you're getting a triangle, you're getting a simplex in x. And then F will take that simplex and will map it into y. But F and G are homotopy equivalent, which means there's a continuous way to deform F into G. So whatever simplex you're getting over here, it can be continuously, so you're getting two different simplices, right? You're getting F of sigma and G of sigma. And the idea is that these two simplices, you can deform one continuously into the other. So even though they might be different, homology-wise, in Y, they should be the same because you can continuously move one into the other. Now, of course, this is not a proof, but it makes it plausible, it makes it believable. But to actually turn it into a proof, it's actually more challenging than it looks like. And we're going to follow the proof that's given by Hatcher. Now, Hatcher, he gives a proof that is a little bit deceptive because his proof is only 1 page long. And if you look at other books, they give proofs that have many, many more pages. That is because Hatcher, there's a lot of reading in between the lines in Hatcher. And that's why Hatcher is not a friendly book for a total newcomer for topology. So even though he does write out the proof, and he does, I think, present the nicest proof that really gets to the point of this, when the proof tends to be too long, sometimes you lose track of what the main idea is. But then the price to pay is there's a lot of reading in between the lines that you have to do to figure out what he's trying to say. And that's what we're going to do. Here we're going to fill in those missing lines. So you can find it in this book. We're going to fill in those missing lines. Now here's the way the proof is going to go. So this is going to be the outline of the proof. So let's start with this. We have n chains in X, n minus 1 chains in X, and n plus 1 chains in X. And we have the boundary operators. And then we have the same thing with Y. We have a boundary operator. We have a boundary operator over here, del and del. Obviously, they're all different maps, but we keep on reusing del because conceptually you're essentially doing the same kind of process in calculating those maps. And we're interested in the n-dimensional homology, and the way we do that is we take the kernel of that and we mod out by the image of this. And we also have maps going like this. This is what we call F star. Okay, this is F star. Actually, let me do it like this. You actually have two maps here. One of them is F star, and the other map is G star. So this is the map which is given by composition. This is what we were saying earlier. If you take a simplex, that simplex gets mapped into a simplex over here by composition. You do F compose G, I'm sorry, F compose sigma, or you do G compose sigma. So there's two different mappings over here. And then you have two mappings over here. Again, they're different mappings, but we reuse the same notation. Okay, so that's like a nice, pretty diagram. And then this is what we're going to do. We are going to define, what so Hatcher calls this a prism operator. So it's the one that kind of goes diagonally across. So you're going to have a prism operator for each dimension. But you have to understand it's going across diagonally. It increases the dimension. So you go from n to n plus 1, from n minus 1 to n, and so on. You'll have, of course, another one going like this, another one going like that. So this P, this is what Hatcher calls this a prism operator. At the moment, we're not saying what it is. So we're not saying what this prism operator is. But this is what we're going to show. So we will show that the prism operator satisfies the following property. That if you do the prism operator composed with del, so in other words, so let's look at this one. If you do the prism operator, so you go like this, the prism operator composed with del, so this, that would be equal to G star minus F star. I know this is a bit unmotivating, like where exactly this comes from, but I'm just saying that let's just accept the fact for now that you have this homomorphism that will satisfy the following property. And then you will see from that property why F star and G star become the same map on the homology groups. So it's F star minus G star plus, and then the other one will be, so let's just understand, maybe it's helpful to actually highlight the composition. So we're doing, I got it backwards. Let me do it like this. P composed, no, the other way around, del composed P. Okay, so let's do this again. You go like this, and then you go like that. Like this, and then you go like that. So we're focusing on the middle piece. That's the one that we care about, because that's the one we want to calculate the homology of, the nth homology of x and the nth homology of y. So we're focusing on the middle one. So we have a map here and the map there. So we're saying that you're doing, you first go P, then you go del, right? So you're getting a map from here to here, and we're claiming that you're going to get this mapping, the G mapping, minus the F mapping. Now, subtraction here just means this is just the difference of the two mappings, because these are, this is a group, so this is just G star applied to an element minus F star applied to the same element. That's just what that means. It's what you say, like the difference of two functions. And then plus, and the other way you can go from here to here is you can take a detour going like this. So you can go del and then P. So then you would just say del composed with P, like that. So that's fairly complicated. But if we're willing to accept this, so if we are willing to accept this, then it is easy to show that the induced map from the nth homology group of x into y and G star are equal. So how do you show they're equal? Well, basically what you do is you pick a cycle, right? So you pick a cycle in Hn of x. Now, of course, when we say pick a cycle, maybe we should say a homology class of the cycle. And we need to show that f star applied to that homology class is the same thing as g star applied to that homology class. So here's the way we do it. So f star applied to that homology class is equal to f star applied to C itself. So the difference between this one and this one is you forget about the class and you just look at its representative C. The representative C is chain, and you're just doing f star applied to the chain. Okay, and then, okay, and now you do g star applied to this. That would be g star applied to C. Now look at what we have. So let's substitute C into this relationship. Okay, so we have that partial prism operator applied to C, right? We're just putting in that C in here. That's equal to G star applied to C minus there's one thing I should have been a little bit more careful about. F star applied to this class is F star applied to C, but it's then the homology class in Y. So I forgot to put in the classes here. And then you would have F star applied to C plus P boundary of C like this. Now, here's the whole point. What are we assuming? C is in the homology. It's a homology class. So by definition, C has no boundary. This is 0. So this drops off. This is specifically because if it's in the homology, by definition, it has no boundary. It's a cycle. So it drops off. And now look at this. So thus, the homology class of this one is equal to the homology class of that one, since the difference of those two cycles, so by definition, two cycles are in the same homology class if their difference is the boundary of something of one higher dimension. And that's exactly what we have. This is a chain of one higher. The prism operator increases the dimension by 1. So this is the boundary of something. And that's what we've proven, that the difference between those two is the boundary of something else. And this is really the idea of the proof. But now we have to do the difficult part, and that is to construct this prism operator. So that's what we have to do next. Now we have to do the difficult part of the proof, and that is to construct the prism operator. And you're going to see why Hatcher calls it prism. So let's start with this. We know that f and g from x to y are homotopic. We have to use this somewhere. Otherwise, the proof would be very suspicious. Now, what does it mean to be homotopic? That means there is a homotopy map, let's call it capital H, that takes x cross 0, 1, and it maps it to y. And then if you evaluate it at 0, you get the first function, and if you evaluate it at 1, you get the second function. That's just the definition of what homotopy between two maps is. So now, what we're going to do is, now what are we trying to do? So the goal is we want to construct a map P that takes an n chain. It maps n chains into n plus 1 chains. And since a chain is a linear combination of simplices, it is sufficient to explain how to do that for a single simplex, because then P will be extended in a linear way as distributing P on every simplex. So sigma is a simplex in X. So we have that sigma is a mapping from the n simplex, the standard n-dimensional n simplex, into X. And we're going to use this homotopy here. But the homotopy is from 0, 1. So we're going to define a map called sigma times the identity. So we have the identity map from 0, 1 to 0, 1. Now the reason why we're doing it is because, I mean, this is going to be the idea. We're going to use the homotopy map to carry the simplex from here to there. So we can therefore use this to construct a new map called sigma cross the identity, and this is going to be a map from the n simplex cross 0, 1 into x cross 0, 1. Okay, and then you have h. So now if you compose everything with h, so maybe it would be better, so let me kind of rewrite this a little bit. So you have delta n cross 0, 1 being mapped to x cross 0, 1. And the name of this map is sigma times I. All this means is that it maps the simplex into x by using sigma, the original sigma, and it maps a number from 0 to 1 into itself. So that's all what this means. You're just extending one extra coordinate because you have this homotopy. And then you have the homotopy map that takes you from that product into y. And now if you do this composition, then you end up with h composed sigma times the identity. But you kind of see what the problem is. This over here, so this is what you're getting. You're now getting something, you're getting a mapping going into y. But you want to have an n plus 1 simplex. You want something of one higher dimension. Now look at what we have over here. This has dimension n. This has dimension 1 because this is just an interval from 0 to 1. So when you multiply them together, right, the product space that you get out of them, this should have dimension n plus 1. The problem is that this is not exactly a simplex. It's not a simplex. It is actually a prism. It's a prism. And what Hatcher does is he takes that prism and he basically triangulates it into many pieces that are simplices, and then he uses them to construct the map. So to show you how this is done, I think you might find it helpful to look at a picture first. So what is delta 2 cross 0, 1? So delta 2, this is just a triangle. Okay, that's just the solid, that would be the solid filled in triangle, but I'm not going to fill it in because it's going to overcomplicate the picture. And then you have an extra coordinate from 0 to 1. So you're just going to repeat the triangle again. Maybe I should draw it like this. You're going to repeat the triangle again. Then maybe this side will kind of make it dotted. So it's going behind. Then we have it go like this, like that. So what you're getting is you're getting a prism. So a figure like this is called a prism. Now, this is what you can do. Let's say these vertices are called V0, V1, V2. And these vertices are called W0, W1, W2. So basically, if you want to say this, you would say that this vertex just, well, let me not rush ahead. So the standard two-dimensional simplex is the convex hull of the standard basis. Now, therefore, these points, this is what happens at 0. So V0, V1, and V2, they would just be the standard basis with an extra coordinate that you just make that extra coordinate 0. So that's all what that would mean. And those points at the top face, that's like the top face of the prism, that would be the standard basis, but now it has one extra coordinate, and that coordinate is 1. Okay, and what we do next is we can triangulate this in the following way. We can start with the convex hull of V0, V1, V2. So you get all of them. Okay, and then you're getting the lower, that's the lower face. Okay, but then you can triangulate in this way. You can say convex whole of V0, V1, but instead of using W2, you go back, you use W, instead of using V, you use W. So you go V0, V1, W1, and then you're getting this. Now, that is homeomorphic to, again, to the standard two-dimensional simplex. That's what we get there. Then we can do the convex whole of V0, W0, W1. So basically, what we're saying is you can use all of the W's, then you can use the first two W's. I'm sorry, you use all of the V's, then you use the first two V's, then you go to a W. You can use one V, and then you continue with the rest of the W's. In this case, you get this. You get that simplex. And then finally, you can use none of the V's and use only W's. Right, and then you're getting that. So you're basically finding different faces here. And you can probably see the pattern. You start with the, you sort of keep the indices going as they are, and then you either, right, you kind of keep the indices going where they are, and then at some point when you decide how many, where you want to stop with the V, you then continue the next index with the W. But I've actually noticed I'm leaving something out. Yes, so this is what I'm leaving out. So I wanted to get something that's one higher dimension. So at the moment, okay, I see what the issue is. Yeah, so I have to have one, like this is fine, but those are two-dimensional. I want something that's three-dimensional, right? Because I'm saying that this is something that has dimension 3. So I want something that's three-dimensional. So sorry about that. I should have included one more. So you can use W0, I'm sorry, V0, V1, V2, and then you go to then you go to W2. So in the picture, this would be this, and then W2. So you would get this three-dimensional solid tetrahedron. So this is where you use all of the V's, and when you run out, you go to W. So when you run out of the V's, that will only give you two dimensions, but now you have an extra one. You have an extra vertex, and that's how you end up getting one dimension. Now you can do the same thing over here. Instead of using, so here, this is what happens if you use all of the V's. The other thing you can do is you can use, let's say, V0, V1, but then you would stop at V1, and then you would switch over to W. So then you would have W1, W2, like that. And then this picture would be V0, V1, W1, W1, and then W2. I'm not sure how to draw that. Maybe, yeah, it'll be some other tetrahedron. I'm not going to try to draw it. And then for this one is, you can use just maybe V0, and then you use the remaining W. So you would have W0, W1, W2. And for the very last one, you actually cannot use the last one. You have to use at least one V0, because if you decide to only go to W, the problem would be is you would not be getting a two-dimensional, a three-dimensional simplex. So you really have to go. So you will not be able to use that one. Okay, so this is what you have. So that's the idea. This is the way you can decompose that prism into various simplices. And now this is the way the prism operator is going to be defined. So we define the prism operator. It's going to go from an n chain in X into an n+1 chain in Y. And here's the way it's going to be defined. And what I'm going to do here is I'm going to switch to a different screen. I actually written notes for this part, and I'll upload the notes on the course page, so it'll be easier for you to read. So let me switch to those notes, and we'll be able to follow this along. And I will provide commentary to how we do this. So this kind of begins the exact same way, that this is the n-dimensional simplex. We're taking the product with the interval. We said this is a prism. And V0 to Vn are the vertices on the lower face. So this is what we had in the picture. More generally, Vi would just be the standard basis element that we're using for the n-dimensional simplex with the extra coordinate 0. And these W's would be the same thing, but they're the ones whose last coordinate is 1. So we start with that notation. And we're going to create this thing called the prism operator. It's going to be a group homomorphism. It will take an n simplex, and it will create an n+1 simplex. And this is what we're going to do. So we have to define what it does on an n simplex. So we choose an n simplex. And so this is the way we're going to define it. And you have to keep in mind that an n+1 chain is a formal sum of simplices. So this is going to be a formal sum. The sum here indicates the correct indices that are being used. Okay, and so it's going to be an alternating sum. So this is what we had before. This is the sigma cross I, and that's the composition. And we're going to those are basically the different triangulations that you're getting. So maybe it would be helpful to return back to the board, so it'll be easier to follow this now. I just like to switch between the screens because when it's carefully written in LaTeX, it might be easier to follow because you kind of see it nicely written out. But the basic idea here is you start with sigma. Okay, you have your homotopy map that takes you from x cross I. Let's write it like this. You have your homotopy map x cross I that takes us into y. And then we have a map. This is sigma. This is delta n cross I. And this is what we're calling sigma cross the identity. And we have this composition, H composed sigma cross the identity. Okay, so we have this. And what we're going to be doing is, we're kind of focusing on this now, we're going to be decomposing those into simplices. So then the way the prism operator is defined on the simplex is going to be equal to, by definition, so this is the way it's defined, is going to be an alternating sum over I. And we indicate that the index will go from 0 to n. We'll focus on the index afterwards, but it's an alternating sum, and it's going to be this composition, and we're going to restrict it. So here's what we need to understand. At the moment, this is a prism. That's a prism. And you can decompose the prism by taking the convex hull of you first use the vertices on the lower face, so V0, V1, all the way up to Vi. So you use I vertices on the lower face, and then you continue with the W's. So then you have Wi all the way up to Wn. That's what we had in the picture. So that's what we do more generally. We need to understand that whatever this thing is, this is this piece down here. This is homeomorphic to an n+1 simplex, because you have, if you count how many you have, you start from 0, you go n over to n, but you're double counting the I. Okay, so when you go from 0 to n, you would have n, but because you're double counting the I, you have n+1. So here we are being actually sloppy. So this is where the sloppiness comes in. Whenever you're talking about n+1 chains, you're getting, let's write this out. So these are formal sums of maps from the n+1 simplex into y. The problem is, and this is where we're abusing notation, is that this is not exactly the standard n+1 dimensional simplex, but this is where the convex geometry portion of the lecture comes in, that even though this is not exactly the standard simplex, there's a homeomorphism from the standard simplex to that we talked about. So really, it's this composed with that, composed further with that homeomorphism, but we do not even bother to write that out because the notation just becomes hideous. So we rather be sloppy and rather have the argument more easily followable, but that's really what we're doing. Okay, so yeah, that's what we have. And as far as the indices are concerned, I can start at 0. So this is where you begin. You always have to choose the first vertex, because if you skip the first vertex, then you only have W's, and you have W's go from 0 to n, and the problem is that's not an n+1 simplex, that's an n simplex. So that's why you always have to include the v0. So at the very least, I has to start at 0, and at the very most, you go all the way up to vn, and then you have wn. So you have that one extra coordinate that makes it be an n+1 simplex. So that's what you're doing here. So this is how the prism operator is defined. So the next thing that we do is, so I'm going to switch over to the screen. Okay, actually, let me tell you what the goal is. So the goal is to show that if you take the boundary of this, right? Remember, we want to show the boundary of the prism operator is the prism operator of the boundary of sigma, and then we have G star of sigma minus F star of sigma, right? That was sort of what we were claiming that makes the proof work out in the end. So we're going to therefore focus on this piece. This is the piece we're going to focus on. So we have to calculate the boundary of this. Okay, we're going to go ahead and calculate the boundary. So how do we find the boundary of something? So the boundary of a simplex, maybe this will make it easier. Let's call it tau. Let's say tau is an n+1 simplex in Y, right? This is now a simplex in Y because it's being mapped with the composition, it's being mapped into Y. So how do you find the boundary of tau? It would be, we're going to use a different indexing letter. This will be J. J will go from 0 to n+1, right? From 0 to n+1 because that's the dimension. You'll have the alternating sum. And then it would be tau restricted to the jth face of, so the jth face of delta n+1. And again, we're being sloppy. What we really mean is the jth face of delta n plus n, there's a homeomorphism with the n simplex, so you have to compose it with that homeomorphism first. But that's too tedious to write out. And this is exactly what we're going to do here. Instead of tau, we have p of sigma. And so the boundary of p of sigma would therefore be equal to the sum. So j would go from 0 to n+1. And you are applying it to the prism, but the prism operator itself is a sum. You see, p of sigma is this entire sum. So you just apply it to that entire sum. So that would be another sum where I goes from 0 to n. You have -1 to the I, you have -1 to the j. So you have I and j, so the I comes from this one, the j comes from that one. So you have an I for the prism operator, that's the way it's defined. Then you have the j for the boundary operator. And then you're going to take this, H composed sigma cross I, which is being restricted to the convex hull of those vertices, but you have to choose the jth face of that. So it's going to be the jth face of the convex hull of all of those vertices. So as you can see, the notation here is absolutely horrendous, but that's why we have to abuse it, otherwise it looks even worse. So what is the jth face? So the jth face would simply mean you would drop off the jth position, right? You would find the jth vertex in this list, you would remove it, and then you have the convex hull of one fewer vertex, and that is going to be homeomorphic to the standard simplex. And you're going to compose it with that homeomorphism, and that's what this is supposed to represent. So maybe if we switch screens here to the notes that you will have, so I'm kind of wrote this out for you so that it's easier to follow than what Alan Hatcher does, because a lot of the stuff that we're writing out, Alan Hatcher does not actually explain it. So we have this, right? So we have the prism operator. As we've said, it's the convex hole from V0 to Vi, and then you can carry on with the same, but with the vertices on the upper side of the prism. Then the boundary operator, the J, goes from 0 to n plus 1. The I goes from 0 to n. Then you have these two factors of -1. You have that composition. And I just wrote, as you can see, because it's really the jth face of that convex hull. So I just wrote the jth face. And what we do next is we're going to split the sum. So this is really like a double sum. You have all possible combinations of I and j. So I ranges from 0 to n, and j ranges from 0 to n plus 1. So you have all of those different combinations. And what we're doing here is we're splitting it into cases where the j is smaller than I and when the j is greater than I. So that's what we're doing. So it's sort of like what you call a double sum. But let's focus on where j is less than I and then when j is bigger than I. Okay, so we kind of split it like this. So let's write it on the other board over here. So we're going to write this as, it's a double sum, but you're going to see why it's convenient. So the motivation for considering two separate cases, so we have this one. So let's just write it out first. And this is restricted to the jth face of that, plus this one, where j is greater. No. So then the other one, so I got the whole thing backwards. I meant to say j is less than or equal to I, and when j is greater than I. And it'll just be the same thing. Restricted to the jth face. So the reason for splitting it in such a way is because you should notice that there's two cases that can happen. These are the V vertices, and these are the W vertices. So when you're taking the jth face, if j is smaller than I, then the vertex that's being deleted from the convex hull is one of the V's. And if j is bigger than I, then j is deleting one of the vertices among the W's. So that's why you have like two different cases that naturally come up over here. So here you have the jth face. And the way I write it in the notes is this is the jth, this is the jth, this is going to be the jth V vertex. So let me just check how I wrote it. So I write it as, I guess I do not even write it in like that in the notes. But basically what I mean is this is the jth one among the V's that you see. And that's precisely because j is smaller than I. So I is basically which of the triangulations that you're using in the prism, and the j is the one that's being deleted. So this is just the jth deletion among the vertices that are called V. Now, something interesting happens with this notation, and this is something that Alan Hatcher does not explain at all, and this might cause a lot of confusion. So this is what we call reading in between the lines. So let's understand what's happening here. J is bigger than I. So to make it a little bit easier to understand, let's pick some concrete numbers. Let's say n is equal to 5. Okay? Let's say that I is equal to 3 and j is equal to 4. Okay? So we have vertices V0, V1, V2, V3, V4, V5. Then we have W0. Well, these are the lower ones. These are the upper ones. W0, W1, W2, 3, 4, and 5. So the 3 indicates the triangulation. So we go up to 3. So we have V0, V1, V2, V3. And then we continue the triangulation with the W's, with the upper vertices. So we have W3, W4, W5. So if you count 1, 2, 3, 4, 5, 6, 7, it's 7, but counting from 0, that's 6. So this is now a 6-dimensional simplex. So we go up in the dimension with the prism operator, but we're choosing the jth face. So when you're choosing, so the I indicates the triangulation number, and the j indicates which face you're choosing. So you're choosing the 4th face. So you have 0, 1, 2, 3, 4. So this is the one that's being deleted. Okay, this is the one that you delete. Now this is why the notation is a little bit unfortunate, that the one that you delete, so j is 4, but the one that you delete is actually labeled 3. So in this case, when j is bigger than I, you are deleting all of the w vertices. But the actual position, the actual index label for that vertex does not actually match the j number, because you're sort of double counting the 3 twice. So what you basically do is you do a sort of a change in summation notation where you make it sort of being off by 1. So what we do here is, so this is the way that I'm going to write this, that we're going to have, instead of j, we're going to have j plus 1. And then instead of j greater, we now allow the possibility that j is greater than or equal to I. But the jth face will no longer mean the jth face counting from the beginning. This will rather mean the jth w face. So that would mean the jth index position for w, the jth w vertex. Okay, so in this notation, what that would mean is, so going back to this example again, if this is what we want to get, then using this new notation, what we pick for j would then be equal to 3. So it does not mean you count from 3. It does not mean 0, 1, 2, 3. It does not mean that. It means it's from the j vertices, you're going to select the one in position 3, and that's the one you're going to delete to get your face. But by doing so, you're offsetting yourself by 1, so that's why this is j plus 1. So this is the way we write this, and all of that is, of course, hidden in the Hatcher book. So that's the explanation. So this is going to be much nicer notation to use. So this is what we now have. The next thing that we do, so maybe I should switch the screen here so we can kind of follow the notes. And yes, so that's basically what I just explained. The I index indicates how many times V is repeated, and the J index indicates which coordinate is deleted. So for example, if n is equal to 5, if I is equal to 3, then we get the convex hull, right? This is the triangulation we get for the prism, V0, V1, V2, V3, right? We go up to 3, and then we continue with the W's. Now, if we set J is equal to 2, we then delete V2 vertex and are left with the so we delete this one, so we're left with V0, V1, V3. That's right, that's what we're left with. However, if we choose J to be bigger than I, so J is equal to 4, then we get the convex hull of, so 0, 1, 2, 3, 4. So you see, we delete W3, and we have W4 and 5. We delete W3. So it's more natural to use the notation where the J matches the one that we delete. So we replace this one, the jth face counting from the beginning, by rather writing J greater than or equal to I. We replace J by J plus 1, and then this one would be the jth W face, where we start counting from W itself. Okay? So that's why we have that adjustment. And then the boundary would be equal to this. So it's basically, we're just replacing. Now, the other thing that I want to say, and this is, I guess, the other important point, is that in the beginning, so I'm not actually saying this in the notes, but in the beginning, notice J ranges from 0 to n plus 1. By doing this change, by making J be 1 larger, so this is J plus 1, by making it be 1 larger, the largest value that J can now take would be n. So in this sum, J at the very most, in this sum, J at the very most could be n. And in the first sum, J can only be n, because I itself only goes up to n. So by doing this change of basically a shift of index, you set everything up so that the I index ranges from 0 to n, and the J index ranges from 0 to n. So that's the other advantage of the notation. It just looks a lot nicer when it's the same range for both indices. Okay, so here we're just rewriting what the boundary, so this is the prism operator. Maybe it would have been better to put an extra bracket around that, because you're first applying the prism operator, and to that prism operator, you're then applying the boundary operator. So maybe you need an extra set of brackets here, but that's the way we've written it on the main board. And here we're just rewriting what this is. So when you rewrite it using this better notation, you're getting this piece where it's the jth W face. So it's the jth one that you're choosing among the W's. Here j less than or equal to 1, here j greater than or equal to 1, and here you're choosing the jth W face. Okay, and now I want to show you something interesting that happens. Okay, so let's switch over to the main screen and continue with this argument. Something very interesting begins to happen when we consider when the indices are equal. So if we take all, let's call them left sums. So we have two sums, the one on the left and the one on the right. If we take all left sums with I is equal to j, when those are equal, and all right sums with I is equal to j, we will get a telescoping effect. So that's going to be kind of cool to see that telescoping effect, but it's going to be very helpful to do it in a specific example, because otherwise it's easy to get lost with the notation. So here, let's suppose the dimension is 5 again, and we're going to pick I is equal to 3, and j is equal to 3. So what kind of, so what is the jth v vertex? So this is the way this, we're going to get the following convex hull. We're going to have the simplex, which is the convex hull of v0, v1, v2, v3. So that's the one that's being deleted. Then we would have w3, w4, w5. And it's the one that's in the third position that's being deleted. Now look at what happens in the other sum. In the other sum, instead of picking I is equal to 3, let's pick I is equal to 2 and j is equal to 2. Then in the right sum, this notation, it will indicate that we have the simplex, which is the convex hull of v0, v1, v2. So we go up to v2, then we carry on with the other vertices, w2, w3, w4, w5. The one that we delete, that's the jth face in the w notation. So that's the one that we end up deleting. So now observe that even though this simplex and that simplex are different, when we end up deleting these two, the remaining vertices are exactly the same. Okay, so when we have 3, 3 here, and when we have 2, 2 here, these are exactly the same. But notice this is I, this is j, this is I, this is j plus 1. So the signs are going to be opposite. So this map will cancel with that map. Okay, and then more generally, if you have, let's say, I is, so you have 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. Okay, so this is I comma j, I comma j in the left sum. So these are the different combinations that you have. And these are the different combinations you have here: 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. The ones that cancel is, well, we just saw that the 3, 3 cancels with the 2, 2. And likewise, 4, 4 will cancel with the 3, 3. 5, 5 will cancel with the 4, 4. 1, 1 will cancel with the 0, 0. 2, 2 will cancel with the 1, 1. The ones that do not cancel are specifically these two. And that's exactly what happens in a telescoping sum. In a telescoping sum, it's sort of like the smallest and largest ones, they're the ones that remain. Because with 0, 0, you do not have a -1, -1. And with a 5, 5, you do not have a 6, 6. So these are the ones that you're left with. Now, what is this? What do we get when we do that? That's going to be the convex hull of we begin at V0, right? We just begin at V0. Well, we always begin at V0, and then we carry through with the W's. So then we have W0, W1, W2, W3, W4, W5. So the I indicates how far you go on the V vertex, and the 0 and the J indicates which one you delete. So you end up deleting the one in the 0 position. But what happens? So, but what is this? You see, the W's are the upper face of the vertex of the prism, right? These are the upper face of the prism. Recall what these W's are. This is E0 times 1, E1 times 1, E2 times 1, and so on. So this is the upper face of the prism. And what are we doing? We are taking the homotopy map, composing it with sigma times the identity, and then we're restricting it to this upper face, the upper face of the prism. So that would be the convex hull of all of those vertices. So in general, up to Wn. So this is what happens at time 1, right? This is at time 1. So really what this is this is H at time 1 of sigma, right? Sigma, this is the identity. Well, this is being evaluated at 1 because they're all equal to 1. And at time 1, that's the G map. So this is really, well, I guess I should have said H composed with that. Yeah. So that would just be G composed with sigma, because at time 1, right, you're interpolating. At time 0, you're getting F, and at time 1, you're getting G. So that's why it's sort of G composed with sigma. Now, in the other extreme case, that's the other extreme case that we with the phi 5. What is that supposed to represent? Well, that's supposed to represent the convex hull, where the V goes up to 5. So we have V0, V1, V2, V3, V4, V5, and then we carry on with W5. And the second one indicates which W face we delete. So that's the one in the 5 position. And this is what we're left with. This is the lower face of the prism. Okay, so, and here, when we compose, so you see, we have this, and then we have this. So in this extreme case, we have 2 extreme cases. Here the extreme case is when they're both 0. Now when they're both 0, this is positive 1, and this is exactly what we said. This is going to be G composed with sigma. Here, in the extreme case, when they're both equal to n, this will be 2n plus 1. That's an odd number, so that would be negative. And then this composition, this is being evaluated at the lower face. This is the homotopy at time 0 on the lower face. And so you're getting the map at time 0, which is F, composed with the sigma, right? It's being composed with the sigma. So if we therefore return back to these notes, so I explained to you again what happens like if n is 5. So if I is 2 and j in 2, the face coming from the first sum is the convex hull of the vertices. So you just write it out and you delete the 1 in position 2. And then you can compare it to what happens when I is 1 and j in 1 in the second sum, right? From the second sum, you get a different convex hull, but the vertex you end up deleting will leave you with the exact same points. So all of this is just sort of commentary to make it easier to understand. This is, of course, hidden in the Hatcher book. And so if you combine, so basically if you take all of the terms where I is equal to j, and you add them with all of the terms where I is equal to j, by only restricting yourself to that special case, you will be left with H composed with this at the convex hull of, those are the vertices on the upper side of the prism, and these are the vertices on the lower side of the prism. So this is time 1, this is time 0, and so you get G, right, the homotopy at time 0, that gives you G composed with sigma, and this is minus F composed with sigma. Okay, so to summarize, this is basically what we've shown. We've shown that when you take the boundary of the prism operator on that simplex, you get G composed with sigma, minus F composed with sigma, then plus, and this is the remaining piece that you have, right? So we've evaluated out the cases when I is equal to J and J is equal to I, right? We've evaluated out those cases separately, and this is what we're left with. Okay, so let's just return back, therefore, to our main screen. So actually, let's remove all of this and start again. So we have defined the prism operator from n chains to n plus 1 chains. And we have shown that if you take the prism operator of sigma and then you take the boundary, you end up getting G composed sigma minus F composed sigma, and then you get some mess, right? Which we're not even going to bother writing up. You get the remaining mess. The remaining mess, this is where you have one of the sums is where I is less than J, and plus another sum where J is bigger than I. J is bigger than I. So that's the remaining mess that you have. But you have to realize what this is. This is exactly what we call G star of sigma, and this is exactly what we call F star of sigma. What are those? Well, going back to our diagram again, this is the diagram that we had before. This is Cn of y, Cn minus 1 of y. Then we have it going like this. This is Cn plus 1 of x, Cn plus 1 of y. We have it going down like that. This is these are the boundary maps. And then we actually have two pairs of maps going down. One of them we call F star, the other one we call G star. That's what we were saying. And F star and G star are just given by composition. And that's exactly what's going on. G composed with sigma, you're going from that simplex to this simplex, and it's given by composition. And that's basically what we've shown. So we've shown that the boundary, so without the sigma, you're essentially saying that the boundary operator composed with P is equal to G star minus F star, right? This is sort of what it's being evaluated on. And then you have plus some extra mess over here. And it remains to show that this extra mess is exactly P composed with sigma. And because this is a graduate level course, and I think our exposition on this proof has been painfully long, the remaining part of the proof is for you to figure this out. So that's your exercise. So this is what we have shown. And then we claim that this remaining sum, right, this remaining sum with these written like that, is precisely the other piece. And when I was writing this, I started writing this out, and then I realized, okay, so this is, I realized I was not showing that to you. Yeah, so yeah, we had this, and as I was writing this out, I realized that I think we did enough. Like, as I was writing that out, I realized this is getting way too long, so maybe I should just be lazy and ask you to justify why that one is equal to the remaining sum. And it's maybe a good way to learn this stuff if you can rederive it yourself. So that completes this very technical proof of the homotopy invariance in homology. So now we'll move to the other, it's totally unrelated theorem, and that's the Horevich isomorphism. Here's the theorem. This is Horevich theorem. Let X be path connected. I know that when we talked about covering spaces, we always assumed our spaces were path connected. When you talk about the homology groups, you do not need to assume that X is path connected, because as you saw on your homework assignment, the zeroth homology group counts the number of path components. So let X be path connected, and you pick some point in X. Then the fundamental group of X at P and the homology group, the first homology group. Now these are possibly different groups. Here different we mean non-isomorphic, because this one is in general not abelian, and this one is always abelian. But when you abelianize this, group, then it turns out that it is isomorphic to the first homology group. This is actually why we want this to be path connected, because if the space is path connected, then regardless of what point you pick, the homology groups will always be isomorphic to each other. So that's very natural why we want this condition. So that's the theorem. So for instance, before we write down the proof, just to show you some examples of this theorem, if X is the figure 8 space, let's say, then we know that the fundamental group of X at some point, it does not matter, but let's say P is the point where the two circles meet. This is a free group of rank 2 generated by the two loops around each of the two circles. So then the homology group of X would be isomorphic to the free abelian group of rank 2. That's Z plus Z. So you're saying that there's supposed to be a basis of two cycles. There's two different cycles you can find in X that will generate all of the cycles. And you can probably guess what those are. That's the cycle that goes around like this, and the other one is the cycle that goes around like that. Right? You can probably guess what this is. So this is like C1, C2, and it's reasonable to guess, though it will take some extra effort to show that the homology group would then be isomorphic to formal sums of those two cycles. That's what we would get over here. Then we also said that if X is the Klein bottle, then its fundamental group does not matter what point you pick. We saw that this is generated by, there's two generators, A and B, but this is not a free group because there's a relation between those generators, and the relation is that AB is equal to B inverse A. And so that would mean that the homology group of the Klein bottle, well, let's see what this is telling us. When you make it abelian, basically what that means is instead of using multiplication, you make it addition. Because that's the notation that we use in group theory, that in general, we multiply, and when we use additive notation, that's when we indicate that things are going to be additive. So you would say that H1 is generated by, you're going to have two cycles that generate for you the groups. And I'm not even necessarily saying, because the vocabulary is a little bit different. There's a difference between a loop and a cycle. I mean, like they're motivated to be similar, but they're not actually the same thing. After all, a loop is a mapping from the closed interval, and a cycle is a formal sum of mappings from the one simplex. So they're not, I mean, if you carefully use the definitions, they're not the same, but similar, right? It's similar. That is going to be generated by, so maybe I should not use A and B. Maybe if that bothers you, maybe I should use two different letters. Let's call them U and V, generated by, you're going to have two cycles, U and V, and they're going to have the property that U plus V is negative V plus U. Okay, and then that would mean that the U cancels and V is equal to negative V. That's just another way of saying 2V is equal to 0, right? That's just another way of saying it. So basically what this is this is going to be isomorphic to the integers, because one of the generators, U, has no relation on it, so it's just essentially a free generator. And then the other generator, when you do it twice, you get 0, so plus Z mod 2Z. And you can maybe check this. Check with your homework computation. You did have a question on the homework to compute the homology of the Klein bottle by using a delta decomposition. So it's recommended to then see if this answer is consistent with what you did on the homework. So this is the Horevich isomorphism. I should say the Horevich isomorphism, well, let me take it back. This is an isomorphism, but there is something called, a little bit more generally, called the Horevich homomorphism that goes from the higher homotopy groups to the higher homology groups. That one is not an isomorphism. If it was an isomorphism, then it would be trivial to compute the higher homotopy groups, but they're very difficult to compute. But you do have a more general homomorphism, and in the one-dimensional case, you actually get an isomorphism. So we're going to discuss the proof of this. So you can say this is the other main result for this lecture. I would argue it's not as important as the first one, but it's a nice result. It nicely shows the connection between the two groups on a topological space. Here's proof. So let's start the proof by defining, well, let's make the following observation. So we first observe that if f is a path in X, so we're not assuming that it's a closed path at P, like a loop at P. We'll do that later, but more generally, let's just assume we have a path in X. Then F is also a one chain in X. So here we're abusing notation, because a one chain is a formal sum from the one simplex into X. It's a formal sum of mappings from the one simplex. Now, the interval and the one simplex are technically different things, but there's a homeomorphism between these two. And the homeomorphism, as an issue of orientation, if we call this x0 and we call this x1, then this is going to be our one simplex. Maybe I should do it like this. This is going to be our one simplex. This is delta 1. And the way we orient the one simplex is we always start from the smaller coordinate and we go to the larger coordinate. So that's the way that we orient it. And the way we orient the interval is we go from the smaller number to the larger number. So as you can see, there's an obvious homeomorphism from one to the other that will take that endpoint to 1, that endpoint to 0. We do not even bother writing what that homeomorphism is. So when we say that F is a one chain, we just abuse notation as we've been doing for the first part of the lecture. What we really mean is F composed with that homeomorphism from the simplex to the interval. Then you've appropriately written it in the form where you're mapping delta 1 into X in this orientation consistent way. Again, the orientation is, of course, arbitrary, but it's just that when we use the boundary operator and all of that, that's just a convention that we use about which one goes first and which one goes second. With that composition, then we do have a mapping into X, and we get a one chain. So this is the first thing you want to realize, that if you have a path in X, then that path is a one chain. It's a one chain in X. And after the first homology group will consist of one cycles. Furthermore, if F is a loop at P, then F is a one cycle. So why is this? So let's check this. To check that something is a one cycle, we take the boundary of the chain. And in general, when we talk about the boundary of the chain, we talk about the zeroth boundary of F minus the first boundary of F. right? That's the way we calculate the boundary operator. Now you can see the 0th boundary. That's what happens when we set x0 is equal to 0, right? That's the 0th face. So we're getting that endpoint minus that endpoint. So in the abuse notation, this is f of 1 minus f of 0. Because delta 0 of f in the picture, that's this endpoint that corresponds to 1, and that endpoint corresponds to 0. So we're getting f of 1 minus f of 0, and this is p minus p, which is 0. Okay, and here we are abusing notation twice. Which, by the way, is very common in this subject. You do not want to write out every detail, because like what you're trying to say is pretty clear, but if you try to make it like properly rigorous with your original definitions, then it just notationally will look worse. We're abusing notation when we're going from here to here, and then we're also abusing notation when we write something like this, because you have to understand this is supposed to be a 0 simplex. A 0 simplex is a mapping from delta 0 into x. So technically, if you look at this, this is not a mapping into x. That's already a point in x. But a mapping from the 0 simplex is choosing a point, and that's just the corresponding point that you're choosing. So we are abusing notation, but it makes sense that the boundary of f, the boundary of that one chain. So if you think of f, so we're kind of switching the way we're thinking here. We're taking a loop. We now think of it as a chain, and we calculate the boundary of that chain, and we see that it's 0. And so that means that f is a cycle. Okay, so we have a map. So we have a map. And the map is that we're taking something in the fundamental group, and then we're mapping it to something in the homology group. And how is that map defined? Well, it's defined very simple. If you take f, and f represents a loop, you simply map the loop to itself, right? This is now a one cycle. So you start with something that is a loop at p, and then you get a one cycle. And there is no at p, because a cycle does not have a beginning or an end. You get a one cycle. Now there is things you need to check. So we do have to check. We do need to verify that the above map is well defined. So in other words, what if you have, because the fundamental group, it consists of homotopy classes. We really want to show that if you take the homotopy class, we want to take the homotopy class of f, so you're choosing a representative, and you're going to map it to the homology class of f. So two different brackets, but the meaning, of course, is different. Homotopy, so it's clear that if you have a loop, if you choose a representative, then that representative will give you a one cycle. But what is not clear at the moment is what happens if you have a different. What if we have a different representative? Then we get a different one cycle. But the idea would be that, yes, even though we do get a different one cycle, the different one cycle we get will be homologous as opposed to homotopic, homologous to the original to the original loop that we have. So that's what we have to justify. So here is how we justify this. So suppose f. So let's say f0 is homotopic to f1, and to understand which one it is, we'll just write in pi 1x comma p. So by indicating the group, we understand this is homotopy classes. So then by definition, that means there is a homotopy map, homotopy map, let's call it H, capital H, that will take us from x cross 0, 1 into, actually, sorry about that. That will take us from 0, 1 cross 0, 1 into X, so that H of t comma S, right? So that H of t comma 0 is F0 of t, H t comma 1 is F1 of t. Okay, this is interpolation parameter 0. You get the first, well, you get the 0th loop, interpolation parameter 1. You get the first loop, and now, and at the endpoints S comma 0, that would be the same thing as S comma 1, that would be equal to P. So that's just the definition of what it means for two loops to be homotopy equivalent. So let's draw a picture. This will make it easier. What are we doing? We are mapping this square into X. We're mapping that square into X. And we're saying that when you set this lower edge, when you set S is equal to 0, the image of that will give you F0, that's F0, and this lower edge, that will give us F1. And these endpoints, well, not the endpoints, but the left and right edges, these all get mapped. It's constant here, and those get mapped to P. You map that into X. And now what we'll do is, if you look at this, maybe you get an idea of what we're trying to show. So if we want to show that F0 and F1, so what are we trying to show? Okay, so what's the goal? So we want to show that F0 is equal to F1 in the homology group. That's what we want to show. So we want to show that these two classes are equal as homology classes. Now, how do you show that something is equal in the homology group? i.e., that if you take their formal difference, F0 minus F1, that would be equal to the boundary. So these are one-dimensional chains, and you want to show that it's the boundary of some two-dimensional chain, of some two chain. And what is a two chain? It's a mapping from the two simplex. So how do we get that? Well, if you look at this homotopy map, this is a square. And you can get the simplex by triangulating it. You just triangulate it. That's the idea. So you get the upper half, right? This is delta 2, and this is delta 2. Now, I know they're not technically delta 2. I know that. They're not the standard geometric simplex, but they're homeomorphic to the standard geometric simplex, as we've talked about. Because if you want to, you can say that this. So let me just show you what we're saying. Like for the upper half, you have these 3 points, right? You have these 3 points over here in the upper half. So this upper half, it's the convex hull of those 3 points. These 3 points are in general position in the plane, and so the simplex that you get is homeomorphic to the standard geometric simplex. And if you compose with that homeomorphism, then you have a mapping from delta 2 into X. Okay? So, I mean, that's the basic idea. And and geometrically, the way we orient these simplices is you make the thumb pointing towards at you. The thumb points towards, so the side that you see is the side that points towards. So this is the side that you see. So you make your thumb be perpendicular, point to you, and if you curl your fingers, you're going to get it going like this. Okay, that's the way the upper one gets triangulated. So we have two maps let's call it U from delta 2 into X, and L from delta 2 into X. So U, that's just the upper, right? That's just the upper one that you see, and it's just you're choosing this homeomorphism with sort of like the standard, with the standard simplex. So the side that's facing you, that's the side that's, I mean, it's almost like a pun at this point, you and the side that's facing you. So yeah, you can just imagine that this is aligned with that one is aligned with this one. So you get these two mappings, and then you will see that the boundary of U would be, you go around the edges, so you have the diagonal map, which I'm just going to call, maybe I'll just call this D for the diagonal. So you restrict U to this one, so you get a diagonal map, then you get minus F1 plus this entire edge. But this entire edge is the constant path that goes to P. So I'm going to abuse notation, and I'm just going to call it P again. Technically, that's not a point. That's supposed to represent, I guess it's negative, right? I mean, I guess maybe I should write negative, because it's kind of going down. When I write P over here, I just mean it's whatever, I mean, this is just a constant function which is equal to P. It's not the point P, it's the constant function that gives you P. And then the boundary of L is, so when you find the boundary of L, you orient, so if we orient it, like this, like we always do, it would go, so I got that backwards, it will go like this, like that. So when you orient it going like this, then you have F0, you have plus P minus D, okay? So therefore, so then the boundary of this formal sum, okay, you can take the formal sum, this is a 2 simplex, that's a 2 simplex, technically mappings of 2 simplexes, and this is the formal sum of them, and then the boundary of the formal sum would then be D minus F1 minus P plus F0 plus P minus D, and in the end, when everything goes away, it's just F0 minus F1. So that's the way that works. So you were able to show that the difference between those two is the boundary of some 2 chain. Okay, so I think this is probably the best way to write the proof, because it is, of course, possible to take this piece and make this more rigorous. But by making it more rigorous, you will have to fill in some extra steps. Like, for instance, you would have to basically change coordinates, get that homeomorphism from this triangle to the standard 2 simplex and all of that. And that's what we call missing the point in mathematics. If you ask any mathematician how they think of this, this is exactly how they think of it. If you ask them to write the formal proof, everyone will draw that picture. And if you still insist on getting more detail, then they will work with that picture to fill in the extra steps. But that's kind of like the main idea of this. So that's why this is well defined. Okay. So let's clear this away and go back to the very beginning. So we're now continuing with the proof. So we have shown that we have a map that takes us from the fundamental group of X at P to the homology group of X, which takes a homotopy class and it sends it to its homology class, that this is well defined. Okay, so we have a well-defined map. Yeah, so this well-defined map is what is known as the Hurewicz homomorphism. You actually have something similar for higher homotopy groups, from pi n to hn. But the isomorphism part comes later. The Hurewicz homomorphism is not an isomorphism. The the isomorphism that you end up getting is when you abelianize it. But with as we remarked, the higher homotopy groups are already abelian. So that's why it's not an isomorphism in general for when you're using higher homotopy groups. So this is what we have. Then the next thing we claim, oh, I forgot something. We're saying it's a homomorphism. So if you're calling it a homomorphism, you better show that it's a homomorphism. So next thing, the next thing to check is that this homomorphism, that this map is a group homomorphism. So here's how we do this. We're going to do this more generally. So here's how we do it. So we're going to write down a lemma here that if f and g are paths in X, so we're not assuming that they're loops. So if these are paths in X and f of 1 is equal to g of 0, so that the juxtaposition is defined. Recall how we do juxtaposition. We first go along f twice as fast, and then we go along g twice as fast. And you need the endpoint of f and the beginning point of g to match in order for this to be a path. Otherwise, that's not a continuous map from the inter. You're not going to get a path. Is defined. So then, so how do I want to say this? So then f star g minus f minus g is homologically, so then this is a one cycle. This is a one cycle in X. So why is this a one cycle? Well, because the endpoint, so what's the endpoint? The endpoint is g of 1. What's the beginning point? F of 0. Here we would do minus the endpoint of f, which is f of 1 minus f of 0, minus g of 1 minus g of 0. And now, if we work this out, you have f of 1 g of 0. You see f of 1 g of 0 minus f of 1 plus g of 0. So we have cancellation over here. And we have cancellation on the other ones. Right? Cancellation with this one, cancellation with that one. So then that is a one cycle. So that's not difficult to see. But furthermore, this one cycle is homologically trivial. So that means this one cycle happens to be the boundary of a two chain. So in other words, i.e., f juxtaposed g minus f minus g is the boundary of some two chain. So there's a nice pictorial proof of this lemma coming from Breton. So Breton gives a nice pictorial justification for this. And of course, it's pictorial, but you can convert it into like a more formal proof, but that's kind of boring, right? Like, it's more important to get the motivation for what we're doing than to actually write out the formal steps. I mean, once you see the idea, then writing it formally, that's the easy part. So this is the nice picture. Let's draw a two simplex. This is x0, x1, x2. And recall what the standard 2 simplex is. This would be these points in R2, in R3, so that the sum of the coordinates is 1. And they're non-negative, but I'll write it out. Xi are non-negative. So when you draw it, it goes like this. So that right there is going to be your standard two-dimensional simplex. And as we said many times before, it's not the tetrahedron, it's just the side that you see. I do not want to fill it in because if I start filling it in, it's going to confuse what we're trying to say. So here's the way you do this. You're going to make this path that goes from 0 to 1. You're going to make this f. That's going to be f. This one is going to be g. The orientation will follow from going from smaller to larger. So you move along this way, that's going to be f. Okay, so we're trying to define a mapping. So when you have a 2 chain, you want to define a mapping from the 2 simplex. You want to define a mapping into x. So here's the way the mapping is going to be defined. If you're on the lower edge, that's going to be f. Of course, what we mean is, we're being sloppy, but we understand what we're trying to say. F is a path. So f goes from the interval from 0 to 1. So you're going to take this lower edge, you're going to homeomorphically align it with 0, 1. And if you have a point over here, that point will homeomorphically correspond to a point on the interval from 0 to 1. And then you just apply the f that you have before. So that's the way you define what it does on this edge. And that's the way you define what it does on that edge. But how do you define what it does from x0 to x1? So here's the way that you do it is you're going to draw perpendiculars. So you're going to like interpolate this with perpendiculars. So here, that's going to be that. I mean, you kind of do it like this. You just interpolate this with perpendicular lines. The lines that are perpendicular to that edge. You just fill this in. And the idea is you make the map on delta 2. So this mapping, so this is from delta 2 into x, be constant. On each, those are basically levels. Maybe you can call them sections on each section. You make it be constant on these sections. So like, for example, so let's pick this one right over here. So this is the one that's highlighted. So on the one that's highlighted, on this entire section, the value of this mapping is going to be constant. We're not saying the map itself is constant, because as you move across these different levels, you're getting different values. But on this entire section, it's going to be constant. But how do you know which one it is? Actually, I realized that the way I'm drawing the picture is not correct. Yeah, not drawing the picture correctly. I guess. Yeah, I mean, I guess the perpendicular one, it would sort of, if you do it properly, it has to hit both of them. So maybe we draw like the one in the middle, going like this, because it has to hit both f and g. So when you're on different levels, so like for instance, if you're located in the middle point, when you go down the perpendicular, you end up getting the point where the f and the g come together. So on this entire bolded red section, it's going to be constant and is going to be equal to f of 1 and g of 0, where they both come together. If you want to know what this mapping is doing on this section, and every single point on that section is going to be constant, and it's going to be equal to exactly where it intersects with g. So whatever g is evaluated at that point, that is how you define it. And so you're basically like interpolating it in with all of those perpendiculars. And you have now defined the mapping from delta 2 into x. And of course, you can figure out the actual formulas for that, but they will probably be messy. And then in the end, what you have is, and then the boundary of this mapping, so we do not even bother giving that mapping a name. That would be equal to, well, it's the three sides that you see. The one that goes along the lower edge, that would be F. Then you have the one that goes along this one, so F, G, so F plus G, F plus G, and minus the one that goes along the third face. But the one that goes along the third face, look at the way it's constructed. As you move like this, right, up to the middle point. So as you move up to the middle point, it takes its values from G, but then it takes its values from F. What is that? That's precisely the juxtaposition. You move along one, and then you move along the other. So that's going to be minus F juxtaposed G. And then look at that. You have shown that this difference, well, here we have it the other way around, but that's not a big deal. So we have shown that this difference, this minus that difference is the boundary of some two-dimensional chain. So, so that's the lemma. So the lemma is that if you have two paths, then this difference is homologically trivial. Okay, so we have justified the lemma. But what are we trying to do? We have to show that it's a group homomorphism. So going back, we want to show that this into X is a group homomorphism. So what do we have to do here? Well, here's the way it goes. We have to, so we need to show that if we take F multiplied by G, so you take a product of two homotopy classes in here, that would get mapped to the sum of the homology classes over here. Okay, so let's work this out. How is this defined? Multiplication is defined by juxtaposition. That will get mapped to the homology class of whatever that is. But the homology class of the juxtaposition, and this is what we've just proven, that is F plus G. Because by the lemma, F juxtaposed G minus F minus F minus G is homologically trivial. Right, so this is a different representative for that. And that proves that we have a group homomorphism. Okay, that's a group homomorphism, but there's still more things to be shown. Now you have to prove that the abelianized group is isomorphic to this homology group. So there's still more work to be done over here. So this is a pretty long proof. There's many steps that one has to do. But let's continue with the other steps. I did look at the clock and I realized that this lecture is becoming abnormally too long. So if we finish the proof of the Horevich isomorphism, it's going to be way too long. But maybe what we can do is we can just say what remains to be done to finish the proof. You can see the completed proof in the Breton book, where he writes it out very nicely. But let's just summarize what we currently have. Summarize. We have a mapping from the fundamental group into the homology group. So we have a mapping over here. We did not give it a name. Maybe we should call it H for Horevich. And how does this mapping works is that if alpha is a homotopy class at a closed loop at P, then it gets mapped to alpha itself. So you could say, if you want to, that you're mapping a homotopy class into the homology class, because this is now a cycle, because this is a closed loop. And we have shown that H is well defined, because we are choosing representatives and all of that, and H is a homomorphism. What do we have to show? The goal is to show that when you abelianize the fundamental group, it's going to be isomorphic to the homology group. Well, recall that if you have some morphism, let's say phi, between two groups, G1 and G2, and phi is surjective, then that would mean that G1 mod the kernel of phi would be isomorphic to the image of G2. I think you call this the isomorphism theorem, or maybe like the first isomorphism theorem for groups, that if you have a homomorphism between the groups, if you find its kernel, you mod out by the kernel, that will establish an isomorphism with the image, but in this case the image is G2 because this is a surjective mapping. And that's basically what's going on over here. You need to understand that this is not the abelianized group, that's just a fundamental group, but the way you get the abelianized group is well, before we go there, let me just first say that you have to show that H is surjective. Like you have to show that H is surjective. Okay, so if we can show that H is surjective, then that would mean that the fundamental group modded out by the kernel of H would be isomorphic to the fundamental, not the fundamental, the homology group of X, the first homology group of X. So that's what we need to do here. So we have to show it's surjective. So this is, I would say, the first thing that you need to do. And the second thing you need to do is you need to actually argue that this is exactly the abelianized group. How do you get the abelianized group? One way of getting the abelianized group is you take all possible, maybe in general, okay, so in general, one way of getting the abelianized group is you do G mod H, where H, this is the subgroup generated by all elements of the form A, B, A inverse, B inverse, where A, B vary over the group G itself. So you would have to show that the kernel of H is exactly that subgroup. So there's two things you need to do here. And because we're going to be running out of time, maybe we'll just give an outline of why H is surjective. Just a very quick outline for why it's surjective. And then hopefully that will satisfy as much of the proof as possible, and then you can read it up in Breton for more details. So we have this map where you take a homotopy class and you map it to a homology class. So why surjective? Okay, so we're going to pick a cycle in H1 of X. So this is a one cycle. Now for simplicity, because I think this is enough to get the point across, but for simplicity, let's say our cycle is a sum of three paths. So we have F1, we have F2, and we have F3. And this will form a cycle because there's no boundary now. Of course, in general, a cycle could be a lot more complicated. There could be a lot of more paths involved that make up a cycle. But let's not go there, right? I think this is enough to illustrate the main idea. And what we do next is we have our base point P. We have our base point P. And what we do is we just draw an arbitrary path from P to whatever the beginning point of that. So maybe we call those paths G subscript. So the beginning point of that path is F1 of 0. We can do that because our space is path connected. So we pick another path to that point. So that would be G F1 of 1, which is the same thing, by the way, as G F2 of 0, and so on, right? You kind of do it for all of them. Now, the reason for doing this is because if you go along this one, then along F1, and then you travel back, you get a closed loop. Okay, so then you would have, if you do F1, so if you juxtapose, if you travel along G F1 0 first, then along F1, and then you backtrack G F1 of 1, so that's the reversal path. This is now a closed loop. This is a loop at P. Right, that's now a loop at P. And then you do something similar for the other one. You do something similar with F2. Then you would do G F2 of 1 F2 juxtapose G F2. This should have been F2 of 0. Of 1, this is a loop. Backtrack, this is a loop at P. And then you do the same thing with the third one. So this is G F3 of 0, G F3 of 1. You backtrack. This is a loop at P, like that. And okay. And of course, if the chain was more complicated and you had more paths that made it up, you just iterate them the correct number of times. Also, chains can have multiplicities, and you just write out the multiplicities that you have. So that's what you do. If any of these were negative, then you just reverse everything, right? You just reverse them. You just reverse the orientation. So that's basically what you do. So you get all of these loops, okay? And now the claim, right? And then we claim that if you were to take all of these paths and multiply them together. So if you do H apply to, so now you take the homotopy classes of all of those. You do G F10 times F1 times G F11 reversal, and you multiply it by the second one. Now the reason why you need these to be closed loops is because in the fundamental group, all of your paths have to be closed loops. So you have to do this kind of maneuvering to turn, the Fs themselves are not necessarily closed loops. So you have to do this kind of maneuvering to create loops that are at P, so that you can generate a loop in the fundamental group that will go to the required element. And then you do the same thing over here. This is G F3 of 0, juxtapose F3, juxtapose G F3 of 1, like this. So we claim that when you apply H to that entire product, that would be equal to the homology class of C, right, where C is all of that. Well, how do you do it? Well, H is a homomorphism, right? So H applied to a product would be a sum, right? It would be a sum. So that would be, now this is the part which is a little bit suspicious, okay? This is the part which is a little bit questionable. What you essentially want to do is you want to say H, well, you want to say H applied to each of these, right? You want to say that H, so it would, maybe I should write it out. So it would be H apply to the first one, then plus H apply to the second one, plus H apply to the third one. It's a group homomorphism, as we've proven. And you want to check that this is equal to C, right? That's what you want to show. And the issue here is that what we want to say, okay, this is what we want to say, is we want to say that this is H. You see, it's sort of like H of a product. So you want to say it's H applied to, but you want to be able to say this is H applied to G F1 of 1 plus H of F1 plus H of G of F11. It's kind of what you want to say. And then the next one, you see the one that follows after that, plus H of G of F2, that this is the reversal, that these are inverses. They're inverse because they're going to be inverses because F1 of 1 and F2 of 0 is the same thing. Where F2 begins is exactly where F1 ends. So these are just, this is with the reverse. So these just kind of cancel away. So when you end up canceling them away, you're just going to be left with F1, F2, F3, right? Which is the chain itself. But the argument is a bit more subtle than that, because being able to distribute H on each of these pieces is questionable, because this is okay, but this is not okay. Because this is not an actual, this is not a closed loop. You see, that's not a closed loop. So one has to do some extra maneuvering to make that work out. But that's like the basic idea of how you do it. Some extra work is required to make that kind of argument work out. But I think that's enough. I think that's almost as closest to the proof that we can get within our time limit. I'll just finish here. You can, of course, look it up in the Brennan book if you're interested. And that should be enough for this lecture.